Welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 5 from the October-November 2008 paper 2. This is from the Cambridge 9709 syllabus, and this question actually is a question in my A-level Cambridge end of topic worksheet on integration, and this is worksheet number 8, and this is question 5 from that as well. And it's to do with the integration of things of the form of 1 over x. Okay, so here we have something which in the AS integration of P1 we were not able to integrate, because normally when you integrate something like 1 over, say for example, x squared, we rewrite it as, x to the power of negative 2, then you add 1 to the power divided by the new power. But if you have 1 over x squared, so if you have 1 over x, that's like, 1 over x to the power of 1, which becomes x to the power of minus 1. And if you try to integrate that in this way, you end up with adding 1 to the power and then dividing by the power, and then it doesn't work. So that was one of the types of expressions we were not able to integrate in P1. So when we learnt further differentiation in P2 and P3, okay, we learn how to differentiate the ln of x. Okay, so we have y equals the ln of x, and we learned that when you differentiate the ln of x, you end up with 1 over x. Okay, and I'm just going to quickly go through the proof of that, because it might be interesting for some of you. So we know that y equals the ln of x means y equals log to the base e of x. If I want to write that in index form, I can say that, e to the power of y is equal to x. So I can say x is equal to e to the power of y, just rewriting that in index form. That's what this means. Log to the base e of x equals y. That means e to the power of y is equal to x. Now if I differentiate this with respect to y first, so I have dx dy equals, now what we learned in differentiating e to the power of something, it stays as it is, it doesn't change, and it's e to the power of y, and there's nothing inside the function that you have to multiply by, so that's the answer. So if we rewrite this as its reciprocal, we will have dy dx equals 1 over e to the power of y, and here we wrote that x is equal to e to the power of y, so we can say dy dx therefore is equal to 1 over x. Okay, so when you differentiate the ln of something, you end up with 1 over that same thing. Okay, so that's something that we derived from differentiation. Therefore the reverse is going to be true, that if you differentiate, if you integrate 1 over x, you end up with the ln of x. Okay, there's a bit more to it though, which I'm going to quickly explain. Alright, so before I actually go to answer the question, I'm going to go into a bit more detail. We know that the ln function has some limitations, that if I have y equals the ln of x, okay, that I know that the ln function looks something like this. It's the reciprocal, or it's the inverse, sorry, of the e function, and we know that it can never have an input which is 0 or negative. So if y equals the ln of x, we have a condition here that x must be greater than 0. Okay, and when we differentiate this, we have dy dx equals, as we mentioned, it becomes 1 over x, as we just deduced the reverse of our differentiation. Okay, so no, actually we just proved that. So, okay, and we also know, supposing I have y equals the ln of negative x. Now for this to be something which is defined, we have to have the input positive. So the x here would have to be less than 0. Now if I differentiate ln of negative x, there's a condition on it that x has to be less than 0 before we can even start, otherwise it's going to be undefined. So when I differentiate this, I'm going to have the same thing as be 1 over whatever's in here, which is negative x, but then I multiply by the differential of what's inside the function, so I differentiate by minus 1, because differential of minus x is minus 1. So I end up with negative 1 over x, positive 1 over x, sorry. Negative and negative give you positive. So what we can see here is that if you integrate 1 over x with respect to x, there are two possible answers. If you integrate 1 over x with respect to x, you have two possible outcomes. Either you end up with ln of x, either you end up with the ln of x, Okay, like in this case, if you integrate 1 over x, you end up with ln of x. Or if you integrate 1 over x, if you think about this one, you end up with the ln of negative x. Okay, so these are the two possible answers of integrating 1 over x. So we differentiate ln x, we got 1 over x. We differentiated the ln of negative x, we end up with also with 1 over x. So there's two possible outcomes for this, but they depend on what the original x was. So this is true if the x was greater than 0, and this is true if the x was less than 0. So how do I combine these two results into one statement? Okay, so we want the, when x is greater than 0, we'll have ln of x, and when x is less than 0, you have ln of negative x. This is basically the same thing as saying the ln of the modulus of x. Okay, and then of course we have to put plus c at the end. So we can see here that these two possibilities can be written in one statement. So basically we end up with the understanding that the integral of 1 over x with respect to x is equal to the ln of the modulus of x plus c. Okay, so that's a result that we should know. It's the ln of the modulus of x. It's important we put the modulus of x there. Okay, and what will that will do? It will prevent the input being negative, because the input could not have been negative in the first place, otherwise it wouldn't have been a possibility. Okay, the input has to only be positive. So if basically if you have 1 over x integrated, then the answer would be ln of x if x was greater than 0, and it would be ln of negative x if the x was less than 0. When you put ln of the modulus of x, it kind of combines those two statements into one. Alright, so that's basically this result which we have kind of proven in a way. Alright, so that's like a bit of background. Now we're going to go into answering the actual question. I like to try to explain things in a bit more detail, especially in case we don't get time in class to go through them in the required detail that helps students understand things better. But if you didn't understand any of that, it's not a big deal. You just have to remember that you have to put the ln of the modulus of x when you integrate 1 over x. So we're going to now apply that to this question. So once we start integrating, we don't write the integral sign anymore. We're just going to have a square bracket. So 1 over x will become the ln of the modulus of x, as I mentioned. Now you have minus. Now this is 4 over 2x plus 1. So here we have a situation where it's a similar kind of idea. Now, what we notice is when you differentiate the ln of something, of any function, so the ln of some function of x, and you differentiate with respect to x, you end up with 1 over that function, just like we get 1 over x. If you, I'm now talking about differentiating. Okay, I'm doing the other way around. So you end up with 1 over that same thing, but then by the chain rule, you have to multiply by the differential of what's inside that function. So I multiply by f dash of x. So I end up with something that looks like this: f dash of x over f of x. So when you have the numerator as the differential of the denominator, or some constant, you can say some constant times the differential of the denominator. Okay, it doesn't have to be a multiple of it, but some constant times. It could be a fraction times it, whatever, right? Then we know that this can integrate. When you see this, this will integrate into the ln of that function. Okay, and then you have to, divide by basically it ends up like this. It ends up the ln of that function. Okay, ends up as the ln of that function, right? And when you differentiate something, you differentiate it as normal, and then you divide by the differential of what's inside the function. So here what I'm going to do is I'm going to write 4 times. Now I'm going to write the ln of the denominator, because I recognize if I differentiate 2x plus 1, I get 2. And the numerator is some constant times 2, right? Some constant times 2, so it's of the right form. If I differentiate the denominator, I have this form that I'm looking for. So if I differentiate this, I'm going to get, if I integrate this, I'll have the ln of the modulus of 2x plus 1. But then I have to divide by the differential of what's inside the function, which is 2. And then I have my limits 2 and 1. It's the same thing that I did here. I said ln, I recognize that you can think of it like this. The denominator, if you differentiate, you get 1. The numerator is the differential of the denominator, so we can use this pattern. When you differentiate, when you integrate this, you get ln of the modulus of x divided by 1, because the differential of 1 is 1, so you get ln of the modulus of x. And here, this 4 and this 2 will cancel out, so you're now left with the ln of the modulus of x minus 2 times the ln of the modulus of 2x plus 1. And we have our limits 2 and 1, and if we want to, we can put those limits in now. We could simplify this first and then put the limits in as you wish. I'll just put the numbers in now. Okay, you can do either way. So this will be the ln of 2. I don't need to put the modulus once I've put a positive value in here. I know it's going to be positive. If I put the modulus, it's going to end up with ln of 2 anyway, right? Minus 2 times the ln of 2 times 2, which is 4, plus 1 is 5, which is 2 times the ln of 5, minus, and then bracket, I'll have the ln of 1, put 1 in here, minus 2 times the ln of, that's 2 times 1, which is 2 plus 1, which is 3. That's going to give you 2 ln 3. So now I'll end up here with ln of 2 minus ln of 5 squared, which is 25. Remember, we can use the power law here. Okay, 2 ln 5 is the same as 2 ln 5 is the same as ln of 5 squared, which is the ln of 25, minus, and here you're going to have ln 1, which is 0, minus ln of 3 squared, which is 9. Okay, so we have ln of 2 minus ln of 25 minus the ln of 9. Okay, so we have to end up with this. Sorry, this is going to be plus the ln of 9, minus and minus is plus. Okay, minus and minus is plus. So ln of 2 minus ln of 25 plus ln of 9, which we can think of as ln of 2 plus the ln of 9 minus the ln of 25. You can be very careful here, minus and minus is plus. I almost slipped up there. That gives you the ln of, if we use the laws of logarithms, these two will be multiplied. So you have 2 times 9, and this will be divided because of the division law. So we end up with the ln of 2 times 9 over 25, which is equal to the ln of 18 over 25, which is what we had to prove. That's right. Okay, so there we have the answer. Now what you could have done if you wanted to is you could have combined these as one. So I'll show you how to do it that way as well, in case you prefer that way. So some people would prefer to do it this way. You have ln of x minus, and I'll write this as a ln of 2x plus 1 squared. So the ln of 2x plus 1 squared, and you have your limits as 2 and 1. Okay, and then they would have combined this. You could have combined these into one statement. So the ln of the modulus of x over 2x plus 1 squared. And now we can put the values of 2 and 1 in. So we end up with the ln of, and have 2 times x, 2 in place of the x, that's 2 over, and 2 in place of the 2, that's going to be 5 squared, which is 25. So the ln of 2 over 25 minus the ln of, and you're going to put 1 over, and this is going to be 2 times 1, which is 2, plus 1 is 3. 3 squared is 9. Okay, so we can combine these into one statement. That's going to be the ln of 2 over 25, okay, divided by the ln of 1 over 9. So divided by 1 over 9, sorry. Just combine them into one statement. And that's going to be 2 over 25 times 9 over 1, which gives you ln of 18 over 25, which is, of course, the same answer. So it's as you wish. You can kind of simplify this into a simpler kind of a log term before you substitute the values in, or you can substitute the values in right from the beginning, and in either case we end up with the same answer. Okay, so I hope that was clear. I went through some of the kind of proofs of how we integrate 1 over x, and then also why we end up with writing the modulus of x there as well. So I hope that was clear and you all understood, and yeah, thank you for watching. Other questions from this paper, if I ever get to answer them, you can find in the playlist that will appear in this top right corner of the screen. Other questions from the end of topic worksheet number 8 on integration from my P3 collection can be found in the playlist over here. My integration P3 answer or integration from P3 kind of like material I'll put over here. P2 and P3 I'll put it all together because really I teach for P3 and P2 is part of P3 anyway. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.